Welcome to Lecture 2 of Module 10. Today we'll study some example cognitive architectures. First, I want you to be aware of a number of surveys of cognitive architectures. And these surveys will give you a much broader and deeper overview than we can achieve here. Then we'll take a very brief look at some of the iconic and pioneering cognitive architectures such as SOAR, ACT-R and Clarion. And we'll also take a more detailed look at the Isaac cognitive architecture, which was designed specifically for a cognitive robot. And we'll finish up by suggesting some more reading and a video to watch. There are several surveys to choose from. The second last one has a short 1 to 2 page description of 20 cognitive architectures. But I especially recommend the last one and the most recent one by Yulia Kotsaruba and John Tsatsas. It's the most recent and the most comprehensive, covering 84 cognitive architectures. Be aware, however, that instead of describing each architecture individually, it focuses on how core cognitive abilities are exhibited by different architectures. We learned in the previous class that there are 3 paradigms of cognitive science, and therefore 3 different types of cognitive architecture: the cognitivist, sometimes called symbolic, the emergent, and the hybrid. This is a diagram taken from the survey by Kotsaruba and Tsatsas. It shows clearly how the 84 cognitive architectures are divided up into the 3 categories. And it also shows some subdivisions in the emergent and hybrid categories. It isn't possible to look at all of these in the time available, so we'll just sample 4 of the 4 most well-known ones. We'll begin with SOAR, one of the most influential and oldest cognitive architectures. Today, it is characterized as a hybrid architecture, but it started out as a cognitivist or symbolic cognitive architecture. The development of SOAR began in 1983 and is still being developed today. It uses rules, sometimes called productions, to represent its knowledge and also to reason about its knowledge. It operates in cycles. First, there is the production cycle. In each production cycle, it fires or executes all the rules that match the information in its symbolic working memory. These rules might update the contents of its memory, so more rules might fire. When rule firing ceases, it enters the decision cycle, in which an action is selected based on the rules that have fired. The action changes the state of SOAR, such that the new state brings it closer to its goal state. The production and decision cycles repeat until the goal is reached. If no action can be taken, we say that SOAR has reached an impasse. To get out of this impasse, it sets up a new sub-goal to resolve the impasse and uses new knowledge from its memory to resolve the impasse. When it does, it stores a new rule in memory to remember how the impasse was resolved. This is one of the ways SOAR learns. Recent versions of SOAR have other forms of learning. By the way, SOAR was originally developed by John Laird and Alan Newell, who we heard about in the previous class, and Paul Rosenblum. John Laird published the definitive book on SOAR in 2012. One of the exercises in this course is to watch a video about SOAR presented by John Laird. You can read a short summary of SOAR in the survey we mentioned at the beginning of the class. Remember to watch the video too. Now we'll take a brief look at ACT-R, another hybrid cognitive architecture. Like SOAR, ACT-R has been around for a long time, and it too is still being developed by John Anderson, Christian Lubert, and others. It is also a production, rule-based system, but in this case, it is modeled after the high-level structure of the human brain. Like SOAR, it also operates in cycles. ACT-R, however, executes just one production in each cycle, matching the information in its buffers, firing the rule, and updating the buffer with the result. Again, you can read a short summary of ACT-R in the survey we mentioned at the beginning of the class. The third pioneering cognitive architecture we will look at briefly is Clarion. Again, Clarion is a hybrid cognitive architecture using symbolic and sub-symbolic representations and processes. Clarion was designed by Ron Sun, and it also has a long history. Ron Son published the definitive book on Clarion in 2016. Clarion has 4 subsystems: an action-centered subsystem, a non-action centered subsystem, a motivational subsystem, and a metacognitive subsystem. All 4 subsystems have 2 levels of knowledge representation. A symbolic level, in which knowledge is represented explicitly, a sub-symbolic level, in which knowledge is represented implicitly using connectionist networks, and the symbolic and sub-symbolic levels interact and cooperate both in action selection and in learning. As before, you can read about a short summary of ACT-R in the survey we mentioned at the beginning of the class. Now let's look a little more closely at another cognitive architecture. This time we'll look at ISAC, once again a hybrid cognitive architecture. ISAC comprises an integrated collection of software agents and different types of memory. These software agents are independent software processes. They run concurrently and asynchronously, and they communicate with each other by message passing. ISAC has activator agents for controlling the motion of the head, arms, and hands, perceptual agents, and a first-order response agent. This provides reactive control based on associations between perceptions and actions. It has 3 memory systems: short-term memory, long-term memory, and working memory. Short-term memory holds information about the perceptual events that are currently happening around the robot. It has a sensory egosphere and an attentional network. The sensory egosphere is essentially a geodesic sphere which represents what is being perceived by the robot in the direction given by 2 horizontal and vertical angles, often referred to as azimuth and elevation. The attentional network selects the most relevant perceptual events in the sensory egosphere. Long-term memory holds information about the skills the robot has learned and its past experiences. And there are 3 types of long-term memory: semantic memory, episodic memory, and procedural memory. Semantic and episodic memory are both forms of what is known as declarative memory. Procedural memory holds representations of the motions the robot can perform. Episodic memory is sometimes referred to as autobiographical memory because the information is about the robot's past experiences and their associations. This information concerns the external situation, that is the percepts from the sensory egosphere, the robot's goals, the robot's emotions, i.e. its effective response to the perceived situation, the robot's actions, the outcome of those actions, some indicator of the value of those actions, that is an indicator of how successful the actions were in the past in achieving a goal, and any reward that was received as a result. Working memory stores information that is related to the task currently being executed. Working memory also represents expectations and future rewards. ISAC achieves cognitive behavior using 4 other agents. In the cognitive control and reflection subsystem, there is the control executive agent for overall control, the internal rehearsal system for simulating the outcome of actions. In the goals and motivation subsystem, there is the intention agent and the affect agent. The central executive agent invokes the skills required to perform a task on the basis of the current focus of attention and past experiences. The intention agent provides the goals, and the affect agent simulates emotion, modulating the decision-making. ISAC works as follows. Normally, the first-order response agent produces reactive responses to sensory triggers. But the first-order response agent is also responsible for executing tasks. When a task is assigned by a human, the first-order response agent retrieves a skill from procedural memory in long-term memory. This skill corresponds to the skill described in the task information. It then places it in the working memory system along with the current percept. The activator agent then executes it, suspending execution whenever a reactive response is required. Now, if the first response agent finds no matching skill for the task, the central executive agent takes over. The central executive agent recalls from episodic memory past experiences and behaviors that contain information similar to the current task. It then selects a behavior-percept pair, and it does this based on the current percept in the sensory egosphere, its relevance, and the likelihood of successful execution. And this is determined by the internal simulation system. The central executive agent then selects a behavior-percept pair. The skill or the know-how from the procedural memory is then placed in working memory, and the activator agent executes the action. To summarize, there are in excess of 84 cognitive architectures. They can be classified as cognitivist, emergent, and hybrid. Cognitivist, cognitive architectures, are often referred to as symbolic cognitive architectures. The most famous include SOAR, ACT-R, and Clarion. The Isaac cognitive architecture was designed for cognitive robotics and comprises most of the components one expects in a cognitive architecture. In Isaac, task execution is handled either by the first response agent or by the central executive agent. Here's some more reading. If your time is limited, focus on the survey by Yulia Katsaruba and John Satsas. And then, here is a video on the SOAR cognitive architecture presented by John Laird.